Did you know the SpaceX Falcon 9 can also land on the moon? Okay, land is doing a lot of heavy lifting there. A more accurate description would be, it's about to accidentally slam a piece of a Falcon 9 rocket into the lunar surface at several thousand kilometers per hour. And strangely enough, scientists are actually excited about it. Why? Because this rare event gives them a chance to study a real high-speed impact on the moon, data that could help improve future human lunar missions. So today, let's find out how a Falcon 9 accidentally ended up becoming a lunar science experiment, and why researchers can't wait for it to crash. The fact that a SpaceX rocket is about to slam into the moon completely by accident just goes to show how unpredictable and fascinating spaceflight can be. So if you don't want to miss stories like this or the latest updates from the world of space, make sure to hit that subscribe button. There's always something incredible happening up there. Anyway, on August 5th, a spent Falcon 9 upper stage is expected to slam into the moon, kicking up a cloud of lunar dust in the process. It's not a mission objective or a dramatic new SpaceX experiment. It's simply the final chapter of a rocket stage that has been drifting through space since doing its job months ago. That stage originally launched on January 15, 2025, carrying Firefly Aerospace's Blue Ghost 1 lunar lander, along with iSpace's Resilience lander toward the moon. After sending both spacecraft on their way, the upper stage was left in deep space with nowhere else to go. Now, thanks to orbital mechanics doing what orbital mechanics does, it's coming back for one very energetic reunion with the moon. According to a recent study, the impact is expected to occur near the Einstein and Bell craters on the moon's western limb, the edge of the lunar disk as seen from Earth. And here's the fun part. Normally, when something smacks into the moon, it's basically the universe playing darts blindfolded. A random meteor comes flying in, and scientists are left trying to figure everything out after the fact. They usually have no idea exactly when it'll hit, where it'll land, how much it weighs, what it's made of, or even the angle it'll strike. It's like hearing a loud crash outside your house and then trying to reconstruct the entire accident from a few dents in the road. This Falcon 9 upper stage, though, is a completely different story. For once, scientists know almost everything before the impact even happens. They know its mass, its speed, its trajectory, its shape, even what's inside it. That's incredibly rare. It's like dropping a bowling ball into a sandbox in a laboratory. You know exactly how heavy it is, exactly how fast it's moving, and exactly how it's going to hit. Now compare that with just waiting for a random rock to fall out of the sky and hoping someone happened to be looking. That's why researchers are so excited. It's one of the few chances they'll ever get to compare their predictions with a real lunar impact under almost controlled conditions. But here's where a lot of people get the wrong idea. The moment they hear rocket crashes into the moon, they picture some Hollywood-level explosion. You know, giant fireball, shockwave, dramatic music, the whole package. Yeah, the moon doesn't really work like that. A typical meteor slams into the lunar surface at around 16 kilometers per second. The Falcon 9 stage, on the other hand, is expected to hit at only about 2.43 kilometers per second. That's almost 7 times slower. Now, 7 times slower might not sound like a huge deal, but impact energy scales with the square of velocity. In other words, speed is the real bully here. Losing a factor of 7 in speed doesn't mean 7 times less energy. It means the impact is dramatically less violent. Instead of instantly vaporizing everything like a high-speed meteor would, this collision is mostly about crushing metal, breaking the stage apart, and digging up lunar soil. There's one more detail that makes this impact especially interesting: the rocket itself. Most computer simulations assume the thing hitting the moon is basically a giant rock, a dense, solid chunk that behaves pretty predictably. A Falcon 9 upper stage is not that. Most of it is actually empty space. It's basically a giant metal tank with incredibly thin walls and one very dense Merlin engine attached to the back. It's the difference between throwing a solid steel cannonball and throwing an empty soda can. Sure, they might have similar sizes, but they squash, break apart, and transfer energy in completely different ways. Because of that, scientists expect the debris cloud to depend not just on how heavy the rocket is, but on its entire internal structure. where the tanks collapse, when the engine separates, and how the pieces scatter could all change the shape of the crater and the plume of lunar dust. So, how did they actually simulate the impact? Well, they didn't just throw a virtual rocket at a virtual moon and call it a day. The researchers built detailed computer models of both the Falcon 9 upper stage and the lunar surface to see what would really happen during the collision. Again, as I said, the rocket wasn't treated as a solid block. Instead, they modeled its hollow fuel tanks and heavy Merlin engines separately. They also assumed the stage had already burned through all of its propellant, so by the time it reached the moon, the tanks would be completely empty. The problem is, there are countless ways a rocket could hit the moon. It could come in nose first, sideways, upside down, or spinning like someone completely ignored the fragile sticker. But every simulation has to start somewhere. So the researchers picked one clean, well-defined scenario. They assumed the Falcon 9 stage had no propellant left, was perfectly vertical, and struck the moon engine first. Not because they're convinced that's exactly what will happen, it's because the software they're using can only simulate impacts that are perfectly axisymmetric. In other words, everything has to be nice, neat, and centered. Computers are amazing, but they still have their quirks. In fact, the authors openly admit this is the biggest uncertainty in the entire study. If the stage hits at a different angle or breaks apart before impact, the results could look quite different. So don't think of this as the answer, think of it as the best answer for one very specific scenario. So what actually happens when the rocket hits? The Merlin engine slams into the lunar surface first, acting like the tip of a giant metal punch. It buries itself into the ground while the rocket's paper-thin tanks begin collapsing behind it. As those tanks crumple, their side walls end up flinging most of the lunar soil outward. A split second later, the back end of the stage reaches the surface, creating a narrow jet of dust that shoots almost straight upward. The whole sequence lasts just 25 milliseconds. Blink once and you've already missed it. By that point, the rocket has essentially ceased to exist. It's been crushed, shredded, and mixed into the lunar surface, so the really interesting part isn't the rocket anymore, it's the dust. That's where the simulation changes gears. Instead of modeling the violent collision itself, the researchers begin tracking every individual dust particle as it flies through the moon's gravity. And because the moon has almost no atmosphere, there's no air resistance to slow anything down. Every grain of dust simply follows a ballistic arc, rising, coasting, and eventually falling back to the surface. The results predict two distinct parts of the ejecta plume. The first is a broad curtain of debris that climbs roughly 15 to 20 kilometers into the sky before spreading across nearly 183 kilometers of the lunar surface. The second is much more dramatic, a narrow central spike that shoots almost straight upward, reaching an incredible 75 to 100 kilometers above the moon. That's higher than the altitude where most commercial airliners on Earth would be. If Earth had no atmosphere, no gravity problems, and somehow airplanes could fly on the moon. You get the idea. The dust cloud changes surprisingly quickly. Within the first few seconds, it's extremely dense near the impact point. After about 100 seconds, it spreads into a wide, pancake-shaped cloud with the central spike sticking out above it. Around 200 seconds, the curtain reaches its maximum size, and by 300 seconds, most of it has already fallen back to the moon. By around 600 seconds, even the central spike has disappeared, meaning the whole event is essentially over within about 10 minutes. Under the right conditions, that plume may even be bright enough to spot with sufficiently sensitive telescopes, especially because the impact is expected to happen near the moon's dark limb, where the contrast is much better. Of course, there are still plenty of uncertainties. Predicting exactly how bright the flash will be, or how much dust gets thrown into space, is surprisingly difficult. The moon doesn't exactly come with a crash test laboratory, but that's precisely why scientists are so interested. This isn't just another crater, it's a rare opportunity to observe an artificial lunar impact in real time and compare the observations with computer models. Researchers hope to learn more about how dust behaves in the moon's weak gravity, how impact plumes evolve, and how future lunar seismic instruments might detect similar events. The data could also help engineers better understand the hazards posed by artificial debris around the moon, something that's becoming increasingly relevant as more countries and companies send spacecraft there. Future astronauts probably won't have to worry about random Falcon 9 stages falling out of the sky every Tuesday, but understanding the risks now is still worthwhile. For scientists, it's a valuable experiment. For the rest of us, it's just a genuinely cool excuse to point a telescope at the moon and watch a little piece of spaceflight history make one final, very dramatic impact. Meanwhile, China is also getting ready to go to the moon this month, but on purpose. As early as August 24th, China plans to launch its Chang'e 7 mission, a robotic explorer designed to search for water ice near the moon's south pole, one of the most valuable resources for future lunar bases. Right now, the Long March 5 rocket is being prepared at the Wenchang Space Launch Site, while the spacecraft itself is going through its final rounds of testing. But Chang'e 7 isn't just a Chinese mission. It's actually carrying scientific instruments from around the world. In total, there are about 24 instruments spread across the orbiter, lander, rover, and even a tiny hopping robot. Several of them come from international partners, all hoping to answer different questions about the moon, or simply prove their technology can survive getting there. So, who's coming along for the ride? Let's start with the surface. One of the more unusual payloads comes from the International Lunar Observatory Association. Despite the fancy name, it's basically a tiny observatory sitting on the moon. Called ILOC, it carries a sensitive Sony camera that will photograph the sky every 3 seconds in both visible and ultraviolet light. And because the moon has no atmosphere, the telescope won't have to deal with clouds, weather, or annoying city lights. It's about as close as you can get to having front-row seats to the universe. Over the course of one lunar day, which lasts about 2 Earth weeks, it'll observe parts of the Milky Way and deep space as the moon slowly rotates beneath the stars. Next up is Russia. The Russian Academy of Sciences is contributing an instrument package called PML-CH7, which includes a lunar dust detector and something called a Langmuir probe. Fancy name, simple job. Together, they'll study the moon's incredibly thin exosphere. That's the wispy layer of dust and electrically charged particles floating just above the surface. The dust detector measures the size and speed of particles as they strike its sensors, while the Langmuir probe measures the temperature and density of the surrounding plasma. It's essentially checking the moon's space weather and how it's constantly being bombarded by the solar wind. Interestingly, this is an upgraded version of an instrument that was supposed to fly on Russia's Luna 25 mission, which, unfortunately, didn't survive its landing attempt. So, here's hoping this one gets a second chance. Italy is also sending something. Its contribution is a laser retroreflector, which sounds complicated but is really just an array of extremely precise mirrors. It doesn't need electricity, moving parts, or software updates that somehow make everything worse. Instead, scientists on Earth can fire lasers at it, and the mirrors bounce the light straight back. By measuring exactly how long that round trip takes, researchers can determine the distance to the moon with astonishing precision. If Chang'e 7 lands successfully, it'll become the first laser reflector ever placed near the moon's south pole. The international collaboration doesn't stop there. Orbiting above the landing site will be LunaCam, a hyperspectral camera developed jointly by the Bahrain Space Agency and the Egyptian Space Agency. Unlike an ordinary camera, it doesn't just take pictures. It analyzes light across many different wavelengths, allowing scientists to identify minerals, water ice, and other materials hidden across the lunar surface. It's also a major milestone for both countries, marking the first scientific instrument from the Arab world to operate around the moon. Thailand is joining the mission as well. Its contribution is an instrument called MATCH, short for Moon Aiming Thai Chinese Hodoscope. Don't worry if that name doesn't exactly roll off the tongue. Its job is to monitor high-energy particles from the sun and cosmic rays passing through the Earth-Moon system. In other words, it's keeping an eye on the radiation environment astronauts and future lunar bases will eventually have to deal with. It's also the first Thai-built scientific instrument to travel into lunar space, making it an important step for the country's growing space program. Finally, there's Switzerland. Scientists from the Physical Meteorological Observatory in Davos are providing a dual-channel Earth radiation spectrometer. Instead of looking at the moon, it'll actually look back at Earth. From lunar orbit, The instrument will measure the energy our planet reflects and emits into space, helping scientists improve climate models and better understand Earth's radiation balance. It's the first instrument of its kind to make these measurements from lunar distance, and if there's one country you'd trust to build an ultra-precise radiation sensor, it's probably the one that hosts the World Radiation Center. So while Chang'e 7's main mission is to hunt for water ice, it's also turning into something much bigger, a truly international science mission.